the center of mass is going to be the point where we can say that it can be balanced if we're talking about the center of mass, or where we can say gravity is acting on it if we're talking about the center of gravity. And the center of gravity and the center of mass located here, I can say gravity is acting at that point. You can do this in a number of ways. I showed you in the last class how to do it numerically. You can also do it physically. If you suspend any object and let gravity pull it straight down, if you draw a straight line down with gravity down the object with a plumb bob, and then suspend it at anywhere else and draw the line straight down, the place where they cross is your center of gravity. And you could suspend it a bunch of different places. You'd always have that one place where they will cross. From your book on the human body, you can see where the center of mass is based on all of different body parts. You can shift your center of mass. So if we're talking about our leg, when it's vertically extended, our center of mass is here above the knee. If you're sitting, now your center of mass is below your thigh and in back of your calf here, not even on your body. So we can change where our center of mass is. We looked at the position of the center of mass. We can also look at the center of mass velocity and the center of mass acceleration. And we're just going to just do that by taking the first and second derivatives. And so we're going to be able to apply the second law to this, and we can say that F net is really equal to MA center of mass. And this is going to be the same thing for circular motion when it's MAC center of mass. So F net's going to be the net force on all the external forces that act on a system. M is going to be the total mass of the system, and this is going to stay unchanged. Our acceleration center of mass is going to be the acceleration of center of mass and gives no information about the acceleration of any other points in the system. So like when that wrench was spinning and going by, we only know that that point was going straight across with no acceleration because it was going the same distance. Or when the lady was diving and spinning, we could just say that her center of mass was feeling gravity, so its acceleration was -10. We don't know any other part of her body what it would be. So some examples. You have a cue ball rolling towards a ball. And usually this all gets put into the momentum part, but I just felt like we couldn't look at gravitation and orbits and Kepler's laws really without considering center of mass. So after the cue strikes the ball, there is no net external force on the system, so the acceleration is 0. So that would mean that the velocity of the center of mass is constant. As long as there's no external forces, that's going to stay the same. It's going to have the same constant velocity. It's then going to collide with another ball. Because there's no external forces, if our system is consisting of both of these balls, the center of mass velocity still needs to be going in the same direction, unchanged. And again, that would mean there was no friction. Another example would be a solid body. So here he lets loose of the bat. As soon as he does, we're going to ignore air resistance and we're going to say this is a projectile. Now the center of mass acceleration is not 0, it's g. And so this velocity is going to change based on this constant acceleration that it feels. So the sum of the forces of all the acting on a system is equal to the total mass of the system multiplied by the acceleration of the center of mass. And we're going to apply this to circular motion in orbits. So it's the center of mass that follows the parabolic path. This is interesting when things separate, when things explode. In this case, you have a rocket that is taking off, and it is stopping firing here and is going to become a projectile. So it means that its path is going to follow a parabolic path. Or maybe it's going to be a parabolic path at this point. Maybe it's firing up to here, probably firing up to here, and then it's separating. So this would be projectile motion. So that means that it has to follow a parabola. But this part drops straight down. That's not a parabola. And this part extends that way. What is a parabola? The center of mass of the two. And so you could look at what the distance is and see that, and this will differ if they're different masses. That these two masses are staying equidistant from each other. So it looks like these are two masses in your book's example. Here's another one. We have a shell launched on a parabolic path. This one's better than your books because a rocket would not be a projectile while it was firing in the first one, right? It's firing here, so it is not a projectile until it stops firing. Shell launched on a parabolic path. At a certain point, it explodes. Those forces are internal and do not affect the path of the center of mass. So you need to have an external force to affect this. So the fragments of the new parabolic path, but the center of mass continues on the original parabolic path. So whatever this was, it's going to continue on it. We can see that they are at every point. If I calculated the center of mass, I would get this parabolic path. The same thing can happen because you can change your shape. You can change where your center of mass is. So when you are jumping in ballet, when you raise your arms and stretch your legs out, that is going to shift your center of mass higher. The center of mass is still following the parabolic path, but it gives the illusion of you floating. You can see how they're showing that the height of her head stays about the same as it goes through. So aesthetically, it looks like they're staying in the air a longer distance. The center of mass is also going to be the point at which things orbit. So for a lot of things, that doesn't really make a difference. If you're talking about the satellite and the Earth, the center of mass between a satellite and Earth is pretty much the center of Earth. If you're talking about the moon and the Earth, the center of mass of the moon and the Earth is not quite going to be the center of the Earth. It's going to be shifted a little bit towards the moon. If you're talking about the Earth and the sun, the center of mass of that system is not quite going to be the center of sun. It's shifted a little bit inside of the sun. If we think about Jupiter, which is our biggest planet in our solar system, the gas giant, the center of mass between Jupiter and the sun is actually outside of the sun. And so the point for their orbit that they go around, the Earth, Jupiter goes around that point, and the sun does too. So when we look at our orbits, it'll look like the sun is staying still in the lab. But if you look at the sun and the Jupiter one, you'll see it going around that point. So both of them are going around the same point. The same thing happens if you're talking about two stars in orbit. So our solar system is actually not the usual case. There are just as many binary star systems as there are singular star systems. And if two stars are orbiting each other, they're going to orbit the center of mass of two of them. So it's not like the one star is going around the other one, unless it's way, way, way more massive than the other one. If they're near the same mass, they're going to go around a point. So we'll say if that one's 2m, so they're both going to go around this point. This is going to be the center of their orbit. And it would also be the center of the orbit of the planets as well, for the most part, because the planet's not going to move it off the point. The way we can change our center of mass is very apparent in how people do high jumps. I'm going to have you guys look at the video on the Fosbury flop, and you'll see that they devised a new way where they actually reduced where the center of mass was so it went below the bar, which allowed you to go higher because there's a limited amount of energy that you can have when you're jumping.